Dear viewers, today we will have a session on introduction to transistor logic circuits. Now, what would be our objective in this session? First of all, we'll try to see what is an integrated circuit, what are the advantages of it. Then we will see the bipolar and the MOS families. Then we will have a look at the transistor logic characteristics. Then we will just have a glimpse of the TTL family, the most used TTL family. Then we will have a look at the TTL parameters. Then we will go for loading rules. So if we talk about digital IC technology, digital IC technology started with SSI, that is small scale integration, which were actually very few gates per chip. So when you integrate components like transistors, resistors, integrate sorry diodes in a very small package, we usually call that integrated circuit. Now after SSI, there was some efforts going on to integrate more into it. So there came up the medium scale integration, where more than 12 to it was around 12 to 99 equivalent gates per chip. Then it started with the large scale and very large scale integration, that is LSI and VLSI respectively, which had tens thousands of gates per chip. Then we have the concept of ultra large scale integration and giga scale integration, where in case of ultra large scale integration, we expect around 1 lakh gates per chip, and in giga scale integration we expect around 1 million or more. So why IC technology? Why we go for integrated circuits? Now, as we all know that integrated circuits are more reliable, which is actually because of we are trying to reduce the external connections from one device to another. Now, if a particular thing is inbuilt inside a plastic package, and if it is functional, then it also requires a lesser amount of power, and the power supplies become very less costly. Okay, so before ICs, everything was discrete. Even transistor, diodes, resistors were soldered on a printed circuit board. The size was bulkier. More power consumption was there. So in order to have a miniaturization, the things were built into a very small space, in a small and in a plastic package, and it turned out to be integrated circuits. Now there are different technologies involved in the fabrication of integrated circuits. I'm just giving a glimpse of it. Now in most of the PCBs that we had used earlier had suffered from a lot of problems like dry soldering. Yeah, there may used to be a crack develops in the bus systems on the PCB. So it used to create a lot of problems once the PCB used to get older. But when the things were integrated inside a small space on a integrated in an integrated form, the poor soldering, the connection break in the connection paths, all these were protected, and other physical problems were also reduced. Then let's have a look at the uh, actual advantage. The actual advantage was the reduction in electrical power consumption. So miniaturized circuit require less power than compared to the discrete counterparts. So when less power supply lesser electrical power is required, then you always have a simpler design of the regulated power supplies. So power supply cost also got reduced. Also, the heat dissipation from the power supply was also reduced due to low current delivery, and the cooling was also low cooling was required. Huge cooling was also avoided, could be avoided. Then we have, if we talk about integrated circuits, these are low power circuits, and the operations are commonly called information processing. The operation that requires high power levels, like uh, high power switching circuits. Even there are certain sections in the regulated power supplies, in the switch mode power supplies, and other type of power supplies where we still require discrete components, because they take a lot of power. They are switching huge currents. So in those type of circuits we cannot go for integrated circuits. Only integrated circuits are used there just to control, say, few controllers are there, which are generating very low power signals, processing low power signals, processing signals from the sensors. All these things can be achieved by using integrated circuits. But when we have a delivery stage or the output stage where we may require switching of high current, where we may have a continuous flow of current, amplification of huge current, then we require power MOSFETs, power transistors, like VMOS. Then we may also require IGBT, insulated gate bipolar junction transistor. All these things are required when there is a huge consumption of current and huge powers are required. uh, Now let's have a look at the logic families. We have the bipolar junction transistor families. Those are DTL, diode transistor logic. Then we have transistor logic. Then we have emitter coupled logic, that is ECL. Use bipolar junction transistor as their major circuit component, and it's very high speed operation. Then we have the MOSFET. We have the metal oxide semiconductor, a field effect transistor. There we have PMOS, we have NMOS, and we have CMOS. We use unipolar MOSFET transistors as the principal component. Okay, let's move on to current and the voltage parameters. Now, here you can see we have a NAND gate, and it is usually a NOT gate, a NAND gate functioning as a NOT gate, since we have tied both the inputs together, and we have a NOT gate connected at the output of this. Now in this case, on the left hand side, we will call this um, driver circuit, and on the right hand side we will call this a load circuit. Now, let us assume that the output of this NAND gate is high. So, we are considering the situation when the logic is high at the output. We have to remember one thing: the output of this is getting connected to the input of this. So, there are actually two sides of any logical circuit. One is the input, another is the output. So we will have to consider the input profile, input voltage profile, as well as the output voltage profile. Now, below here we can see there is two profiles drawn. One is the output profile, one is the input profile. The output profile means we have something, the voltage range at the output, and when it is getting into any logical gate, then this side is the input voltage profile. So let's have a look at the voltage profile. Here you can see when we consider the output, you can see we have a high when it is between 2.4 to 5. So in this case we can we can just have a few terminologies which can be used here. We can see VIH minimum. So when the output is high, we are talking about this range which is between 5 to 2.4. So we will define something called VIH, and within bracket it's minimum. So what is this? We will just see high level input voltage. It is the high level input voltage. That means VIH. Now I here means the input voltage. That means we are considering something which is here, the voltage which is coming into this particular load TTL, we will call that VIH. Okay, now why mean? The minimum voltage level required for a logical 1 at an input, any voltage below this level will not be accepted as high by the logic circuit. So what does this mean? See, if we have a look at the input here, the range is between 5 to 2. So a voltage, when the output is high, the high logic is conveyed to the input of this load TTL. Here the window says the input voltage will be treated as high if it is between 5 to 2. Now if the input voltage goes below 2, then it is an invalid input. So the range is between 5 to 2 for input profile. Now here the 2, that is 2 volt, is actually the input voltage, high input voltage, which is minimum, beyond which it will enter into a invalid zone. So we will call this the worst case input voltage. So that is why we have just written minimum. So 2 is the minimum, it can't go below this. Okay, now when the driver output is high, a current will be coming out of the system into the load. So if we talk with respect to the driver, this will be called the source current, and here the current is getting into the system, we can call this a sinking current. So when you are talking with respect to the driver, in this particular situation the current is getting out of the system, it is sourcing current. And here we can say VIH, YH, because the current is entering into the system when the logic is high. That is why we are calling it IIH. It is the high level input current, the current that flows into an input when a specified high level voltage is applied to that particular input. Now similarly, if we talk about the output of the NAND gate here, then VOH is the output voltage when the logic is high. H means high logic, and again we are having a minimum. Let us have a look at this. It is high level output voltage, the minimum voltage level at the logic circuit output in the logic state 1 under defined load conditions. Now what does this mean? Now when the output is high, if it is high, then the valid range is 2.4 to 5. So if it is 5, then it's fine. But what is the minimum voltage that we need to consider? That is 2.4. So in this case, when the output is high and we are considering the minimum, that is the worst case voltage, that will be 2.4. So in the case of driver circuit, VOH minimum is the worst case voltage when the logic is high, beyond which it may enter into an intermediate zone or the voltage range becomes invalid, this particular the next TTL gate will not be able to understand what type of logic voltage is that. But you might have observed a difference between the two voltage ranges. We will define that little later. Now again, when the output of the driver is high, definitely it is sourcing current. So IOH, in this case, it is the output current when the logic is high. Now let us look into the low level. So when we are talking about the system which is the output is low, here the current will come from the load into the driver system. So in this case, if we consider the input side of the load, then we will have a IIL. IIL is the low level input current, the current that flows into an input when a specified level voltage is applied to that particular input. Now, in this case, the current will leave this device and enter into this device. That is, it will leave the load and enter into the driver. Now, the voltage that appears here is called VIL. Now, in this case, we will consider the maximum voltage. Now, why the maximum voltage? Now, let us try to understand. Now, since we are considering the input side, we will have a look at the input profile. Now, in this case, when is the valid input? The valid input is between 0 volts to 8 volt. So, if it is 0, then it's fine. This particular load TTL gate will consider that as low logic. But if the voltage somehow increases, then till what will that be acceptable? Now, when it increases till 0.8, till then it will be accepted as low logic. So 0.8 here is VIL, but it is the worst case voltage, beyond which again it will enter the invalid zone. So VIL here we will consider the max voltage, which is 0.8. Now let us have a look with respect to the driver. So in this case, VOL max is again the output voltage when the output is at logic low. Now we'll have to again see the range. Now when we see the range, 0.4 to 0 is the valid range. So when we are discussing with respect to the output of any TTL gate, the voltage range under low logic will be considered valid if it is between 0.4 to 0. If the output is 0, then it's fine. It is accepted as low. But if the output voltage increases, till what it will be accepted? Up to 0.4. If the output is 0.4, it is acceptable. But that particular again voltage is called the worst case voltage, and we will call that max. That is why we have written VOL max. And again, IOL is the current that is entering into the system, that is entering into the driver. If one of the NOT gate is connected, then only one current, that is IIL, will be equal to IOL. But if there are multiple outputs connected, then all the current components will get added and it will enter into the system. So we will define all these things when we study the load parameters or the loading rules, when we study the loading rules. Fine. Now let's move on. This is the very important part. We will again go with a numerical example to understand the loading rules, but let us just have a look at what fan out means. So from our previous discussions, we have already understood that when a particular driver TTL is at high logic, a current will source out of the system. It has been shown by the yellow arrow marks. So we can see a current is getting out of the system if there are these many loads connected. Then depending on the consumption of each and every load TTL IC, the current will get added up. So suppose this is this is high, suppose this is taking 10 microampere. So there are presently there are say 4 not gets, then the total current will be 40 microampere. Since this is consuming 10, this is consuming 10, this is consuming 10, this is consuming 10, so this particular IC will then deliver 40 microampere. Now let us take this example where when this is high, it is delivering 10 microampere to this and to this. So if there are 4 connected, then obviously it is driving the driving current is around 40 microampere. Now this particular driver should be capable of providing that particular current without degrading its performance. So what we can say is the fan out or the loading factor is defined as the maximum number of logic inputs that an output can drive reliably. So this is the output which can drive the next TTL loads reliably under both the situations, that is high as well as low. Now suppose when this is low, current from each and every NOT gate, NOT gate here is shown as the NOT gate, will get into the system. Now suppose each and every NOT gate is giving back 1 milliamperes of current. So there are 4, then the current that will enter into the system is 4 milliampere. So under the situation when it is low, it should be capable of handling that 4 milliampere also. So only under this situation when it is capable of driving 4 as well as in the high state, and also capable of taking 4 when the output is low, then we will call that fan out. So again, I will define fan out is defined as the maximum number of logic inputs that can be driven by a driver TTL logic gate and with complete reliability. We will clear out all the confusion which is arising in this particular slide in the last slide of this particular session, where we will take up a simple numerical example in order to calculate the fan out or the loading factor. Now let's move on to the next. Now what is a propagation delay? The propagation delay, we can just see we have provided an input where the zero state changes to 1 state, and it takes some finite amount of time. Now the valid inputs will be just when it crosses 50%, and this particular zone will be considered high. So what happens in propagation delay when a particular circuit is given an input? What is the time duration it takes to respond to it? So here we can see we have already provided an input, but this particular output is taking a finite amount of time to respond to that particular input. Here we can see we have TPHL. We are considering this with respect to the output. We have TPLH. Now TP means the propagation time and HL means high to low. Here TP again is the propagation time and it is low to high. So this is what is the definition related to the terminologies used for propagation delay. Now let us move on to power requirements. Now let us have a look at this example. Now before we go deep into this particular example, I just have to mention one thing. Whenever we use a supply voltage to a particular integrated circuit, which is basically out of constructed out of TTL, then we will call that usually we call that VCC. But if this particular system is designed out of CMOS or MOS logic, then we will call this VDD. Now, in this case, we have taken an example of TTL. So a particular IC is having three input NAND gates, and there are three NAND gates available. So when we consider the output, there are two possible extreme situations. One is when all the outputs are high, then the maximum current is flowing through the system, and when the output is zero, when the least amount of current is flowing expected to flow through the system. So all other is between that. So what we will do is, to get a sense of the power that is required, what we need to do is we need to consider the situation when output is high, all the outputs are high. So we will call that ICCH, that is the current flowing into the system when all the outputs are high. That is why we are calling it ICCH. And here we will see we are calling ICCL when all the outputs are high, but extremely sorry, when all the outputs are low. So it is ICCL, the L here means low. So what we'll do is we'll take the average of this, that is ICCH plus ICCL by 2. So this gives us the ICC average. Now to get the power requirements, we just have to calculate PD average, that is the ICC average into the supply voltage. Now let's move on to the very important part, which is called noise immunity. Now, what is noise immunity? See, any stray electrical and magnetic fields. Suppose we have a circuit whose one of the output that is seen from here, that is one of the output of the NOT gate is connected to another input of a NOT gate, and suppose these two belong to different IC, different integrated circuits. So when this is one of the integrated circuits, this is another integrated circuit. So in order to establish a connection between them, we need to connect a wire, or we need to have a bus or a copper bus which is built on a printed circuit board. So whatever it is, if we have a wire or a bus system, that particular wire can very well act as a very good antenna. So any stray electrical or magnetic field around the particular device can induce a voltage into those connecting wires between those logical circuits. We usually call those unwanted induced voltage as noise. So this connecting wire behaves as an antenna. Stray electric and magnetic fields will induce a voltage into this wire, which we will term that as noise. Now let us have a look at what happens. Why have we taken a window profile of this, where input profile voltage ranges are different compared to the output profile voltage ranges? Now let us see. Now suppose we have a situation where the output of the driver is high. So a voltage is applied, and a wire has been connected to the next NOT gate, and some stray noise has been picked up by the wire. Now when the output is reaching the input of this, we have VIH. So when we consider the input, we have VIH. So when we are considering VIH, which is this, it can cause the noise, can cause it to enter into the invalid zone. Fine. So when we are talking about the worst case situation, here the worst case situation is 2, but it will all depend on the driver voltage. Now let us have a look at the situation here. When the noise, due to the noise voltage, when the output is low, the voltage can increase from point 0.8 into the invalid zone. Again, it will depend on the output of the driver, the state of the output of the driver, whether it is low or high. So what we will do is how to see the noise margin. In this case, you just have a look at the high voltage range. Now, in this case, the output is valid from 5 to 2, and the input profile is valid from 5 to 2. Extremely sorry. The output voltage profile is valid from 5 to 2.4. The input voltage profile is valid from 5 to 2. So between these two, that is 5 and 2, you can see this is the worst case voltage, which we have called VIH, and this is the worst case voltage when the output is at its minimum during the high state or during the high state logic. So the difference between these two, see, there is a difference of 0.4. So when the output is getting connected to the input, there is a window difference of 0.4. So if the output is at worst case, and when it reaches the input of the TTL gate, and even if that becomes 2.3 volt, see, the input profile says it is valid till 2. So there has been a margin provided under worst case situation, where again we are establishing a compatibility between TTL and TTL with a noise margin of 0.4. Similarly, if we consider the low state, here again you can see when the output is low, the worst case voltage is 0.4. So when it is connected to the input of another TTL, somehow if the voltage increases, say the voltage has increased from 0.4 to 0.5, then again the input profile says it is valid till 0.8. So again here we can see there is a margin of 0.4. So this is called the noise margin when the state is low, at low logic, and this is called the noise margin when the state is at high state. So now let's have a very close look at the invalid voltage range. So if we are considering the output profile, the invalid voltage ranges from 0.4 to 2.4, and if we consider the input profile, the invalid voltage ranges between 0.8 to 2. Now let's see what is current sinking and sourcing. So whenever a driver gate output is high, it will source out current, but whenever the driving gate is at low, it will sink current. So whenever a driver is giving out current, it is sourcing out current, and whenever the output of that particular driver gate is at low, it will sink current from the load gate. So let's move on and have a look at the TTL logic family, where we will just have a look at the standard TTL. Now in standard TTL, what we can see, this is a internal structure of a standard TTL, where we have a few sections that need to be discussed. In this case, we are considering a NAND gate having two inputs, A and B. But this particular section, which is the input, is usually constructed out of an NPN transistor. You can see this is N, this is P, and this is N. But this particular transistor is called polyemitter transistor or a multiple emitter transistor because it is having multiple emitters. Now, if we go for a diode equivalent model, you can see this is a N, P, N. So if I consider just one, then I can just draw a diode where N type is A, P type is connected here, again B is N and P type is connected here, and this side again we have a P and N. So we again have a diode in this fashion. So this particular Q1 transistor can be replaced by a diode equivalent model, which is given here. Now we again have a output section which we call totem pole output. Now in case of totem pole output, when one of the inputs is working, say Q3, when the Q3 is on, Q4 will be off, but when Q4 is on, Q3 will be off. So this is the internal structure of a standard TTL NAND gate. Now let us have a look at how it functions. Now, in this case, we are considering a situation when A and B are both at +5. Now, we have replaced the Q1 with a diode model. Now, you can see here one side of the diode is at +5 and it has been biased by the resistor R1 with +5. Another side is also biased with +5. So there is no voltage difference between the input, that is the N type and the P type. Hence this particular diode D2 will be in the non-conducting state. Similar situation is true for the diode D3, where the input is connected at +5 and the input here means the N type is connected to +5 and the P type is connected to +5 again via the resistor R1. So both the diodes D2 and D3 are isolated, or we can say it's not conducting. But have a look at the diode D4. The P type is biased to +5, the other side is at lower potential, hence this particular diode will conduct, and a current is expected to enter, a base current is expected to enter this particular transistor, which will switch on the transistor, and we will see a flow of collector current flowing from collector to emitter through this particular path. Now when the collector to emitter current is flowing here, it branches into two. One of the current is flowing through the R3 resistor, getting a drop which is more than 0.7, and a current is also entering into this particular transistor, which will actually switch on this particular transistor. Now when a current is flowing through the collector to the ground, actually the the transistor is in switched on mode, and the voltage across it will be almost zero. So if it happens, this particular transistor will be switched off and the output will be virtually cut off from the internal supply voltage, and since Q4 is switched on, this particular terminal X will get connected directly to the ground and we will get a low output. So as we all know that it is the only situation in case of NAND when the output is low, that is when both the inputs are high. Now let's have a look at another situation where any one of the input is switched on. So in this case diode D2 is again off because the N side is connected to +5, P side is connected again biased through R1 to +5. So this is actually in the non-conducting state. But what about this? What about the diode D3? In this case the N side is connected directly to ground and P type is directly biased through +5. We will expect a current to flow through this, and this section will be completely off. So if D4 is off, when we do not expect any current to flow through this, it will directly switch off the transistor Q2, as the base is devoid of base current. So this particular transistor will be off. We will expect a a, a, a larger voltage here. So when we have a larger voltage at the collector, it will switch on the transistor Q3, as well as it will receive a base current which is biased to R2 into this particular transistor, and a voltage, a current will be expected to flow into the output X. Now, when the Q2 transistor is off, there is no current flowing into this particular section of the circuit, so switching off the transistor Q4. So the X is now connected to the supply voltage, and the output will be at logic high, but the output will not be almost equal to the supply voltage. It will be, the output will be less. The drop across diode D1, the drop across the transistor Q3, and the drop across the resistor R4. So output will lie between 2.4 to 5. So we can say the output as at high state. Now let us have a situation when both the inputs are left open. Now sometimes people say, okay, we have not connected the inputs at all, so I can assume I have given a zero logic at the input. But it doesn't happen in case of TTL. Why? Let's have a look at it. So suppose we have kept it open. Now if we have kept the input open, both the diodes are obviously off because one side of it is unbiased. So this particular diode is off. When it is off, the diode D4 is on. It will again switch on the transistor Q2, switching off the transistor Q3, and when Q2 is on, it will switch on the transistor Q4, which will actually connect X, that is the output, to the ground. So during this situation, we will get an output 0. So if we refer to the table of TTL NAND gate, we can see that the output is low only when both the inputs are high, but we have left the inputs open. So the internal circuitry is assuming an input, and we call this floating input. Now let's again have a look at the current sourcing and current sinking. In this case, we can see that we have a totem pole output. Say suppose this can be the output of a NOT gate, and it is getting connected to input, that is can again be a NAND gate. So the output is driving one of the sections of the poly emitter transistor. See if this happens, if the output is off, then obviously this is low. So when this section is getting connected to ground, this particular diode, that is N and P, will get forward biased, and a current will come from the load gate to the driver gate. So this we will call as sink current with respect to the driver gate. So what happens when the driver gate is on? When the driver gate is on, the current will flow from the output of the circuit to the input of this, but remember this will be very less. This is why the sinking current is more compared to the sourcing current, because this particular, when this is high, this particular diode will be biased at high. Since the other side is also biased at high, we will expect a very low leakage current flowing into the system. It will be in microamperes. Now let's move on to the different families of TTL circuit. Now when the TTL was first introduced into the digital logic systems, first it was designed as standard TTL. We also call that high speed TTL, and the power dissipation of it was 22 milliwatt and 6 nanoseconds. And we usually denote that using 74HXX. Now XX means it can be 01, it can be 02, it can be 03, depending on what type of logic gate you are using. But here H means high speed TTL. So this is the internal circuit diagram of the high speed TTL. Now why do we call it high speed TTL? In this case, the values of the internal resistances are so chosen that it reduces the time constant or the time required for any input to reach the output. So it speeds up the system. But if we reduce the resistor values, what happens is there is an effect of v square by r on the power, where if we reduce r, power increases in the square terms of v, that is the voltage applied across it. So whenever we try to speed up the system, we are actually increasing the power dissipation or the power requirement of the system. Now let us have a look at the low power TTL. In case of low power TTL, the values of resistors were increased in order to reduce the power consumption. But when we increase the internal values of the resistors, what happened is the time constant or the stray capacitance and the resistor together form a time constant which increases the charging and discharging time inside the circuit. Again it impacts the speed of this particular family of TTL gate. So what happened was the power was reduced to 1 milliwatt, but the propagation delay increased to 35 nanoseconds, and we usually denote that using 74L. Now in order to boost up the speed, uh, every transistor was equipped with Schottky TTL, which boosted the speed to around 100 megahertz, but the power dissipation or the power requirement was around 20 milliwatt, and the propagation delay went down to 3 nanoseconds. So in this case, it was 74. We denoted this as 74XX, where S means the Schottky TTL. Now, since the Schottky diode was integrated with the transistor, it was denoted as the symbol was redenoted as a transistor having a S at the base. So we replaced all the symbols of the transistor using the Schottky transistor, and this is how it looked. Now let us have a look at the winner. The low power Schottky was actually the winner, where the advantages or merits of Schottky and Schottky TTL and the merits of low power TTL were combined together, and it gave a system which used only 2 milliwatts, and there was a propagation delay of around 10 nanoseconds, and usually it was denoted as 74LS. Now let us now try to understand. We are on the last leg of this particular session. Now we try to understand what are the loading rules or how to calculate the fan out. So see, we have seen 4 sections in TTL family, where we had high speed TTL, that is called the standard TTL. Then again we have the low power TTL. Then we have the Schottky TTL, and then again we have low power Schottky TTL. But in all these cases, the input and the output profile are different. Now let us have a look at the input and the output profile of a standard TTL, where the output profile says when it is high, it can source out a maximum of 400 microampere, and when the output is low, it can take or it can sink around 16 milliampere. And if we consider the input profile, then if we consider single TTL, standard TTL, then it when the input is high, it will consume around 40 microampere when the system is at high state. and when the system is at low, it will give out 1.6 milliampere. So similarly, in low power TTL, we can see it is 200, 3.6, and input profile it's 10 micro and 0.18. And in case of Schottky TTL, it is 1 milli, 20 milliampere output profile, and it is 50 and 200 milliampere for the input profile, as well as low power Schottky, where it says the output maximum sourcing is possible is 400 micro, maximum intake is 8 milli. When we consider the input TTL, the input TTL says that the input of the TTL says the current is 20 microampere, and when the input is high, it will only consume 20 microampere, and when the input is low, it will give out 0.36 milliampere. So keeping this in mind, let us try and understand, if we have a standard TTL, that is driver is also standard TTL and load is also standard TTL. So we will have to consider both the situations, when it is high as well as it is low. So in this case, we can see when a single driver is driving a single load, then when the output is high, it can give out 400, but since it is driving one, its requirement is only 40. So when one of the NOT gate is connected, you can see it requires only 40 to work. Since the output is high and only one is connected, then 40 microampere will source out of the driver. But how many can we connect then? See, the output maximum sourcing current is 400 micro. So if we connect 10, then we will have 400 microampere flowing out of the driver TTL. So this is the maximum limit of number of TTL gates that we can drive when the situation is high. Now let us reverse it. If the system is low, then what happens? When the system is low, and if one of the gate is connected, that is only one load has been connected, then it will give out 1.6. So 1.6 milliampere of current will come out of the load and will be synced by the driver. Now how many then it can handle? It can handle 10. So if 10 are connected, then 1.6 into 10 will provide 60 milliampere. So 60 milliamperes of current will enter into the system, that is the driver, and we can see it can handle 16 milliampere when the output is low. So in this case, both the situation, whether it is high or low, it is successfully and reliably driving 10 standard TTLs. So the fan out in this case, as per the loading rules, says it is 10. So fan out in this case, it is 10. So I would suggest all my viewers to mix up the driver and the load TTL NOT gates and see what happens, and what happens when you what type of fan out you get when you mix the load and the driver TTLs with the different family members. So, and this to summarize, in this particular session, we had a very basics of digital integrated circuits. We had seen the different families in bipolar as well as MOS families. Then we went on to see the characteristics of transistor logic. Then we had a very brief idea and very few specifications related to TTL family, where it included standard TTL, that is the high speed TTL. Then it had low power TTL. Then it had Schottky TTL. Then we had low power Schottky TTL. Then we had discussed certain TTL parameters. We also saw the working of TTL NAND gate. Then we had an idea about the floating input. And again, lastly, we had a very good example on loading rules, that is the calculation of fan out using a simple uh, numerical example. And also, I would request the viewers again to mix the driver and the load logic gates and check out the fan outs. I have already provided you the input and output profile of all the families that we have discussed. So, thank you very much for giving me a patient hearing. And in this particular session, we had covered very basics of TTL circuits. So, thank you again. Thank you very much, and stay tuned for the upcoming videos on CMOS logic. And if you people have not subscribed to my channel, you can go and subscribe my channel so that you get regular updates on the coming videos regarding analog, digital, embedded systems, microprocessor systems. Then I also make videos on consumer electronics, automobile, and other related to it. So thank you very much again for watching this video.